I'll introduce Axel Alpay, the lead of HipSYCL, for his presentation. So over to you, Axel.
Thanks, Tom. Yeah, so I'm going to talk about the latest feature in HipSYCL. So some of you might have heard that HipSYCL recently has announced that it's going to rename to OpenSYCL. This is now the new name has come off sort of legal dispute. So for now, we're going to stick to HipSYCL. So please don't be confused. And yeah, let's go ahead. So I'd like to talk about the use case first. And the use case is deployment of binaries. So let's consider use cases where SYCL binaries need to be deployed and run on systems where we don't know the hardware configuration ahead of time. And of course, this is maybe not a super common use case in HPC, where you usually know your HPC cluster that you want to run on, you know what hardware it has. But it may be very central for vendors of software who then want to distribute their binaries to their end users. And those end users might run arbitrary hardware. So in this case, a single binary needs to be able to run whatever the binary finds on that system. So how is this addressed in current SYCL implementations? First, let's quickly recap how the Clang LLVM architecture very roughly looks like. So you have your source code that is then processed by the Clang front end. So the Clang front end parses the code, generates an AST, also does some checks whether your C++ is any good. And then in the end, it generates code. And it doesn't generate machine code directly. It first generates an code in an intermediate representation, in this case, the LLVM IR. And this intermediate representation has the advantage that then LLVM optimizations can work on it and be implemented in a more or less backend independent manner. So then the LLVM stack starts running its optimization passes and then ultimately runs the backend code generation that actually generates the machine code from this LLVM IR. So how is this typically extended now to heterogeneous architectures such that the binaries can run on GPUs? And the model that is used here is what the SYCL specification calls SMCP, which stands for single source multiple compilation passes. And this is what basically every SYCL implementation to this date uses, and also heterogeneous compilers outside of SYCL use, such as NVCC from CUDA also uses this model. And the idea here is that we have our SYCL code, and in order to create a device binary containing the device code, a special device compiler is invoked, and that device compiler looks for kernels inside your source code, and then generates the device code for those kernels and emits some device binary. Now, if you want to have different device code formats, such as first you might want to have SPIV, but then you might also want to have PTX for CUDA devices. Then you would invoke that device compiler multiple times. So first to generate SPIV, then another invocation to generate PTX, and so on and so forth, until ultimately you also invoke the host compiler. And that host compiler would do a regular C++ compilation, except that it is also fed with the device binaries you have created previously and embeds those into the host binary, such that you have a fed binary in the end that has the device code embedded inside. So what are some issues with that approach? So first and foremost, parsing modern C++ code can be expensive, especially if you have something like our SYCL.hpp header, which contains a lot of templates. And as we add more backends and support for more hardware, then the compile times do not necessarily scale well, because this could mean that we need to now add an additional device compilation pass here. If we want to generate SPIV, we already need one, then we may want to generate PTX, so we need another one, then we want to add another backend, so we may need another one, and so on and so forth. This doesn't scale well. Then it gets even worse, because there are backends such as ROCm that do not have an intermediate representation. So it means that if we want to create a binary that actually can run on all the ROCm GPUs, we need to have one device compilation pass for every single GPU that ROCm supports. And if we add all the different passes together that would be necessary to create a binary that runs on all the hardware that HipSYCL actually supports, it would be around 40 device compilation passes, one for the host, one for SPIV, one for PTX, and then 37, 38-ish for all the ROCm GPUs. And this is not a HipSYCL problem. It's exactly the same issue also for DPC++. And so we can conclude that this is arguably very difficult and inconvenient, maybe even impractical, then to create such a SYCL binary that is universal and can be deployed and then run on any hardware. So can portable interchange formats such as SPIR-V help here? The issue with those formats is that they are not universally supported. So you cannot just tell CUDA, hey, please accept this SPIR-V. But at the same time, it's very important for us and our users that we actually support CUDA and ROCm as backends, because our users still generally want to say that, hey, if I have an NVIDIA GPU, I want to do backend interoperability and call, for example, cuBLAS for NVIDIA's optimized linear algebra implementations. So we still need to have our vendor-specific CUDA and HIP backends that do not support these interchange formats. So what could we do? So the idea here is that, well, I mean, clearly, if we had a single binary device format that is shared across all our backends, then we would at least be able to, instead of having all of these multiple device compilation passes, we could compress those to one device compilation pass that would generate our shared device binary format. But we could even do better, because we could also merge the generation of this shared device binary into the regular host compilation, so that in total, the code would only have to be parsed a single time. And this is basically what we've done in this paper that I'm presenting here. So here we are presenting the very first single pass SYCL compiler, and I mean single pass in the sense that the SYCL specification uses also this terminology, in the sense that the source code is only parsed once. And it's also the first SYCL compiler with a unified code representation across the backends, meaning a single device binary that's embedded in the application that is then shared across our CUDA, HIP, and level 0 backends. And all of these developments, they are already publicly available as part of the HipSYCL implementation. So if you clone the HipSYCL repository today and build it, then you will get this functionality that I'm talking about here. So what is this new model, the single pass compilation model? The SYCL specification calls it SSCP, which stands for single source, single compiler pass. And you can think about it somehow as illustrated here. So you have your SYCL code, which is then fed into a unified compiler, which passes at once. That compiler then just generates IR, as Clang would usually do. And then inside that IR, you find your kernels, you extract your device code from that IR, you process in a form into a form that you can embed it, and then that device binary then gets embedded into your host code, into your host binary. So ultimately, this means that code is only parsed once. In theory, it allows for faster compile times. And this is not a new idea, but it's rarely used. The only major production compiler that uses this approach is the NVC++ compiler. In SYCL, this has never been done before. And there's one small asterisk to that statement, and that is that there are actually implementations of SYCL as a library for NVC++. In particular, this includes the motorcycle implementation, as well as our HipSYCL NVC++ compilation flow. But I would make a parenthesis about these special cases, because in this case, SYCL doesn't provide the SSCP compiler itself. It just comes as a side effect of using NVC++, and the SYCL portion of the world then has very little control over this SSCP compiler. So this is our idea here. We combine SSCP with a generic code representation. And this means that we only need to parse the code a single time, no matter how many devices we ultimately need to run on. And this potentially can significantly improve compile times. At the same time, it also means that we can do analyses and optimizations and also implement new features such as kernel fusion in a way that is backend independent, which allows us to accelerate development. And also, it's a straightforward way now to extend HipSYCL to new hardware, because all you would need to do is to take that generic code representation and find out how you can actually transform it to something that can run on your new hardware. How would this work in practice? Well, in practice, you would do this in a runtime compilation step. So at runtime, your generic code would be transformed to something that can actually be run, and the application would adapt its code at runtime to whatever is found on the system. So how does this work? So we talk about it by distinguishing two stages. So stage one is what typically happens at compile time when the target device is not known yet. And at stage one, during the regular host compilation, we clone the LLVM IR, and we find the kernels inside that IR and extract them and boil it down to only the code that is needed for the kernels. Then we massage that IR to make sure that it's a bit more device friendly and doesn't contain any unsupported features and so on and so forth. And then we embed that LLVM IR bitcode inside the host application. And then there is stage 2, which is executed when the target device is known, where we take the generic LLVM IR and compile it to a backend specific format that we can actually execute. And this is also where the main compiler optimizations for kernels take place. Now, one thing that I get asked about frequently is, hey, isn't LLVM IR a bad choice for this because it's not a stable format? And my answer to this is that, well, I mean, it's true that it's not 100% stable. LLVM IR generally can be ingested by newer LLVM versions, but the reverse is not necessarily true. But this concern mainly comes, I think, from the OpenCL world, where if in an OpenCL, for an OpenCL application, you would have the situation that you would need to pass on your device code to many different OpenCL implementations that come from different vendors that maybe rely on entirely different compiler stacks. And this is a very different situation than what is happening in our case. In our case, our own compiler generates the IR, and it's then exclusively accessed and processed by our own runtime to something else. So in principle, it can be seen as an implementation detail because it never leaves the control of our own stack. There's also one small potential issue, and that is if you want to link together, say, an application and a library that were compiled, that both use SYCL, but they were compiled with a different version of HipSYCL and LLVM. But that scenario already is not supported today because the HipSYCL runtime doesn't guarantee a stable ABI. So basically, using a more stable code format here would only inject additional steps into the compilation flow without bringing additional benefit. So there are also some difficulties when implementing such an SSCP compiler. And one that I'd like to talk about is the case of specializing code paths. And this is important because, for example, users may want to have optimized code paths for particular devices, or also the implementation itself may want to utilize that. For example, you could imagine that if you want to implement the SYCL sign function, you would want for your device code, you would want to map it to some device built-in, while inside the host code, you would want to map it to, say, the regular C++ std sign function or something like that. And in the SMCP world, this can be easily done using macros. You have multiple compilation passes. You can set different macros during those compilation passes, and then you can check those inside your code. But in SSCP, this doesn't work because the code is only parsed one single time. So how do we solve it instead? As it turns out, in SSCP world, it's more useful to think about this problem in terms of control flow. And you would instead express this using an if statement. And this if statement would depend on a special variable, which is what we call an IR constant, which is a global variable that's not a C++ constant, but will be turned into a constant by the compiler later on once we actually know the value that it's supposed to have. And this is, for example, is an idea that's similar to, for example, SYCL specialization constants, except that IR constants could potentially be seen as one concrete mechanism to implement SYCL specialization constants. And since these IR constants are seen as constants for the optimizer, we then can just run additional dead code elimination and constant propagation passes, and then ultimately no branches will be left in the code anymore. We either have the device side or the host side of the code. This is our full stage 1 compilation workflow. I don't want to go too much into detail here. So the red boxes are what happens usually in a client compilation. The blue boxes are what we do additionally to generate the device code. And the green boxes is additional operations that we perform on the host code. And basically, the idea is here, we fork off the host LLVMIR to transform it into some device LLVMIR. One important step here is that we set the stage 1 IR constants to configure this code to be device code. And then on the host side, we configure the code to be host code. And then ultimately, again, we embed that device code inside the host code so that we again have a fat binary. So, and this is what our stage 2 compilation workflow looks like. This we call it also the LLVM to backend infrastructure, because the goal here is to transform our LLVM IR into some arbitrary backend specific code. It consists of a core driver library, which is here in light blue. And then there is one library per backend that does the backend specific stuff. And there are also tools provided to carry out the stage 2 compilation manually, which is useful, for example, for debugging, but also for third parties who may want to use our infrastructure to also translate our generic code to something else. And what happens here? So generally, the process is started when the SYCL runtime registers a miss in the kernel cache. So there's a kernel that's not yet been compiled. Then we load the device code. We configure these the IR constants for the target device. And then ultimately, we invoke the backend specific libraries. And what they do need to do a very important step, which is handling for backend specific LLVM flavors, because in theory, LLVM IR is backend independent. In practice, almost all offload-based LLVM backends have their own conventions regarding kernel calls, how kernels are marked, how address spaces are handled, how built-ins are mapped, and so on and so forth. And all of this is handled here at this stage. Then afterwards, once we have this flavored IR, we optimize it. And then in the last step, we translate it to something that the backend can actually understand, which for AMD would mean we invoke hiprtc. And for SPIV, it would mean we invoke the LLVM SPIV translator. And for PTX, it would mean we use the LLVM PTX backend. So what is the current support? We support this for NVIDIA, Intel, and AMD GPUs. CPU support is planned, and not all SYCL functionality is supported yet. So at the time of submission of the paper, atomics were not yet implemented. They are now fully implemented and supported across all the backends. Group algorithms are now work in progress, but SYCL 2020 reductions and some extensions are not yet supported in that flow. Okay, now let's talk about some results. As I've said initially, this is maybe something that's particularly interesting for use cases where you want to deploy binaries to end users. So the test hardware here is inspired by that, by selecting 2 notebooks. So this one is a notebook with an AMD APU, and this is a notebook with an Intel iGPU and a dedicated NVIDIA GPU, and one workstation with an AMD Radeon Pro 7 GPU. And the benchmarks are Babelstream, a memory benchmark, Cloverleaf, a memory-bound 2D hydrodynamics mini app, as well as MiniBute, which is a compute-bound mini app, and then the RSBench and XSBench applications. And of course, you can find all the details on the compiler versions and the software stacks that were used in the paper. So let's look at compile times first. What I've shown here is the compile time for Babelstream for different compilation flows that we support. And our baseline is our host compilation flow, where HipSYCL acts just as a library for Clang, for the Clang OpenMP compiler. So here, no SYCL-specific compiler logic is running. This is our baseline. Now, if we compile for one AMD GPU with our old SMCP compiler, then, as we can see, compile times as expected go up. Then if we add another AMD GPU, compile times go up further, and so on and so forth, until we have here some results for 3 AMD GPUs. This shows the results for NVC for our NVC++ compilation flow, which is interesting because NVC++ is also a single pass compiler. And this is the compile time for our new compiler. And as you can see, it's only got roughly 20% overhead compared to a regular Clang host compilation. And as it turns out, this 20% overhead is not even due to our additional compilation passes that we've added, our additional compiler logic that we've added. It is our additional compiler logic only makes up around 0.5 seconds. So it would be like something like here if we only included that. It's actually due to the OpenMP front end, and I've not yet found out exactly what is going on there, but there seems to be some interplay with some OpenMP optimizations that it wants to do with the headers, and you can basically disable that using -f no OpenMP, and then it drops down to basically the post compile time. And one thing that's very important to realize here is that even though the compile times for the new generic compiler are lower than for the other compilers, it supports much more hardware, right? It supports all of the AMD GPUs, all of the NVIDIA GPUs that we support, Intel GPUs, while this one here only supports like 3 AMD GPUs, the binary that comes out of that. And as I've said, to support all of the hardware that's supported here, you would need something like 40 compilation flow, 40 compiler passes. So Babelstream is maybe a simple case. So what happens if we use a more complex application like Cloverleaf? Well, basically, we see the same pattern. That's the message here. All right, so now you might say, okay, but Axel, maybe you've cheated. Maybe you've just shifted the compile times to runtime now, and this is now where you're paying the cost. And I would argue then that, well, I mean, if you do it the old way and do the 40 compiler passes, then you might actually do more work than necessary, because not all of your users are going to have like all of the 40 GPUs. Maybe you'd only have needed to compile for 10 GPUs or something like that. So you might have done too much work actually in that case. Also, it's important to realize that the stage 2 compilation that happens, it doesn't compile source code. It compiles LLVM IR, which means that in any case, the code does not need to be parsed again. So you've really removed all of the parsing cost except for parsing it one time. And also, it's important to realize that even in SYCL implementations today, there is already runtime compilation taking place in general. Whenever you have an IR like PTX or SPIV that you want to run and you give it to your compute driver, the driver will then at runtime translate that to machine code. So this is already something that's happening, and SYCL applications need to already expect runtime compilation overheads and deal with that today. So the question is, are the overheads that we introduce so significant that now all of the existing handling of applications breaks down? And so we've also addressed this in the paper and looked into this. And what we found is that our additional compilation logic can be expected to add around 0.2x to 1x of the existing runtime compilation overheads to the first kernel invocation. So that means that, yes, there is an overhead, you can measure it, but it's not like orders of magnitude more than what's already there. So now let's look at performance. And what you see here is the performance for the various benchmarks. And I've normalized the performance results to our old SMCP-based compiler, except for the Intel case, where our old SMCP compiler was actually not mature enough to run most of these benchmarks, which means that our new compiler is already more mature for Intel than what we had previously. And what you can see here is that in most cases, we are within 10% to the existing compilation flows. But there are also cases where we outperform the existing compilation flow. And so overall, we are within -13% to +27%. And one other thing to add is that, as was mentioned by Michael this morning, on Monday, I had my very first hands-on with the Intel Ponte Vecchio GPU, and I tried that on Ponte Vecchio. And basically, I found that I only had time to run Babelstream, but I found that, yeah, you basically get the same behavior also on Ponte Vecchio, and it also matches DPC++ performance there. All right, and overall, these are preliminary results because development focus so far was on functionality, not on performance. And I've put very little effort into optimizing this so far. So conclusion. So what we've seen is that we basically can get significantly lower compile times, especially when targeting multiple backends or devices, and we want to generate such a universal binary, while also retaining the performance and getting instant binary portability to all of this hardware. We have now a single binary that can adapt its embedded device code to whatever it finds on the hardware. And basically, we return to the old mantra, compile once, run almost anywhere, almost because we don't have backends for everything, but for most of the GPUs at least. And it's also a robust platform to extend HIPSYCL to new hardware or implement new features. For example, profile-guided optimizations, kernel fusion, or specialization constants in a backend independent manner, because we just have to operate on this generic code representation. And this is publicly available and works today even with more complex applications like Cloverleaf. And it's also more simpler for users, because now users can just say HIPSYCL targets equals generic, and the binary will work. So yeah, in summary, the world's first single-pass SYCL implementation and the world's first SYCL implementation with single unified code representation that is shared across its backends.
Great. That's great. Thanks. Thanks, Zach. So any questions for our speaker?
If you go back one slide, is the performance for the compile times or the runtime?
Oh, sorry, this is runtime.
So basically there's no difference in runtime performance?
Yeah, so the message here is that you get the same performance as with the SMCP compiler that SYCL implementations use today, but compile times are much, much lower, and also the portability of the binary is much, much better.
Super, thank you.
Well, excellent work. I think it's really interesting. And my question is the following: going through the standards, to the SYCL standard, it appears that SYCL is thought as a two-pass or a several-pass compiler model, right? So, do you think that, for instance, these constants that you are using, should it be standardized in some way? Should it be part of the standard, or do we need even more changes to the standard for this?
So I don't think that the standard prescribes a particular compilation model. What the standard says, though, is that if you use an SMCP compiler, then you need to, for example, define the SYCL device only macro in your device path. And because all SYCL implementations to date have used this model, it has kind of transpired into SYCL user code, where you will find quite frequently use of the SYCL device only macro. So I think that the SYCL implementation should make some statement about what should happen in an SACP case, how users should be able to then reason about which device am I running on, how can I specialize code paths, or maybe even think about, can we generalize this device only macro and the IR constant logic that we have here.
Have you thought of making this an extension? Like maybe that way it will be more clear to the users that they should be using these constants in their code to...
You mean like a SYCL extension? Or?
Yes.
Yeah, I mean, it would be the next step to discuss in the working group how this could work. So we in HIPSYCL, we have already mechanisms that generalize both to the SMCP case and the SSCP case for specializing code paths. But it's difficult actually to generalize to have something that generalizes both to macros and to control flow in a way that's not ugly.
Okay, thank you very much.
Final question.
I'm trying to understand the performance gain, where the gain is coming from. I assume the first stage you remove some like hardware or some specific information. So how the performance could it be better than the case where you have more information in the first stage?
You mean like why we get performance boost here?
Yeah. So again, I was trying to understand, where the gain is from versus the case where you have more information in the original case. Like
why do you think we have more information in the original case?
Because you have some like each of the target has maybe you can have like a more specific information.
But I mean, at this point when we run the code, right, we know which hardware we want to transform our generic code into something optimized for, right? So we want at this point, when we run, say, Minibute on a Radeon GPU, we know when the code starts, okay, we're going to target Radeon GPU, and then we are optimizing the embedded code for that particular hardware. So, and the reason I think why there can be such differences is because the compiler flow is quite different compared to the SSCP case. So the order and of the optimizations that are applied is different. So here we do, in the SACP compiler flow, we do quite a lot of optimizations at the LLVM-IR level. We inline very, very aggressively. And then the code is passed to HIP-RTC, which also potentially does something to it that is not present in the earlier SMCP compiler. So it's just very different processing steps that are applied to the code.
Thank you.
Okay, I think in the interest of time, we'll have to hold the questions there. Axel will obviously be around, so do ask Axel for more information offline if you need it. So we'll thank our speaker once more. Thanks, Axel.